Welcome to this lecture on principles of ecology. Today, we are going to explore a fascinating topic called intraspecific population regulation. Have you ever wondered why a forest is not completely overrun by deer, or why a pond does not overflow with fish? Nature has a built-in mechanism to keep populations in check, ensuring that no single species exhausts all its resources. Let us dive in and understand how this delicate balance is maintained. To understand how population regulation works, imagine a popular pizza restaurant that has just opened in your neighborhood. When it first opens, there are plenty of empty tables, the service is incredibly fast, and everyone gets as much pizza as they want. But as more and more people crowd into the restaurant, the wait times get longer and people start getting frustrated. The restaurant can only comfortably hold a certain number of people. In nature, a habitat is just like that restaurant. When animals are few, food is abundant and they multiply rapidly. But as their numbers grow, they start competing for limited resources, which naturally slows down their growth. Now that we have an intuitive understanding, let us look at the formal definition. Intraspecific population regulation refers to the biological processes by which a single species controls its own size. The prefix intra means within, so this is entirely about individuals of the same species interacting, not about outside predators. As the population density increases, internal competition for essential resources like food, water, and nesting sites intensifies. This intense competition triggers what we call density-dependent mechanisms. This means the regulatory effects get stronger as the population gets more crowded. Ultimately, these mechanisms cause birth rates to drop and death rates to rise until the population stabilizes. Understanding this concept is not just theoretical, it has profound real-world importance. Without intraspecific regulation, populations would grow exponentially forever, which is physically impossible in a finite world. If a population of deer never stopped growing, they would eventually eat every single plant in their forest, leading to mass starvation and ecosystem collapse. This concept is absolutely crucial for wildlife managers and conservationists. By understanding these regulatory mechanisms, we can figure out exactly how many animals a nature reserve can support. It allows us to predict population crashes, manage hunting quotas responsibly, and ensure endangered species have enough space to recover safely. To see how this works mathematically, we must look at how birth rates change as the population grows. This brings us to our first formula, which models reproduction. The symbol B represents the actual per capita birth rate at any given moment. The symbol B0 is the maximum possible birth rate, which only happens when the population is tiny and resources are unlimited. The variable N stands for the current population size. Finally, A is a constant that measures how strongly crowding reduces the birth rate. In plain English, this equation tells us that as the population N gets bigger, the actual birth rate, B, goes down because of the crowding penalty. Just as births are affected by crowding, so is mortality. Let us look at the second equation, which models the death rate. The symbol D represents the actual per capita death rate of the population. The symbol D0 is the minimum possible death rate under ideal, uncrowded conditions. The variable N again represents the current population size. The constant C measures how much crowding increases the death rate, perhaps through disease transmission or starvation. Physically, this means that as the population N gets bigger, the death rate D goes up. Eventually, the rising death rate and falling birth rate will meet. When the population reaches a point where the birth rate exactly equals the death rate, the population stops growing. This brings us to our next formula, the carrying capacity, represented by the symbol K. The carrying capacity is the maximum number of individuals the environment can sustain indefinitely without degrading. In this formula, the numerator, B0 minus D0, represents the maximum possible intrinsic growth rate under perfect conditions. The denominator, A plus C, represents the combined strength of the density-dependent effects on both births and deaths. If the environment becomes harsher, the crowding penalties increase, which physically decreases the overall carrying capacity. Before we move on, let us see this with a concrete example. Imagine a population of rabbits living in a large meadow. We are given a maximum birth rate of 0.8 and a minimum death rate of 0.2. The crowding penalties are 0.002 for births and 0.001 for deaths. We need to find the carrying capacity to know how many rabbits the meadow can support. We substitute our given values into the carrying capacity formula. The numerator evaluates to 0.6, and the denominator evaluates to 0.003. Dividing these gives us 200. This means the meadow can sustainably support exactly 200 rabbits. Now that we have used this formula successfully, let us understand where it comes from. We are setting out to prove how the carrying capacity formula is derived from our basic birth and death rate equations. We start with the intuition that at equilibrium, the population is stable, meaning the birth rate exactly equals the death rate. We substitute our linear equations for B and D into this equality. Next, we use simple algebra to group the ideal rates on the left side and the density-dependent terms on the right side. By factoring out the population size n, we isolate the variable we want to find. Finally, dividing by the combined crowding penalties gives us the exact formula for carrying capacity we just used. So we have proven that our carrying capacity holds at 200 rabbits. This brings us to an important question. What is happening when the population is currently at 150 rabbits? Let us calculate the exact birth rate at this specific moment. We use our linear density-dependent equation for the birth rate. We plug in our ideal birth rate of 0.8, our penalty of 0.002, and our current population of 150. Multiplying the penalty by the population gives a reduction of 0.3. Subtracting this from the ideal rate gives a final actual birth rate of 0.5. The mothers simply do not have enough food to produce as many offspring as they could in a perfect environment. Following our birth rate calculation, we must now calculate the actual death rate for those same 150 rabbits. We use our death rate equation and plug in the minimum death rate of 0.2 along with our death penalty constant. Multiplying the penalty by 150 gives an increase of 0.15. Adding this to the ideal death rate gives us a total actual death rate of 0.35. Because the birth rate of 0.5 is still greater than the death rate of 0.35, the population is still growing. This makes perfect physical sense because 150 is still below our carrying capacity of 200. Now that we have calculated these rates, let us visualize the entire concept in a diagram. Here, you are looking at a graph of density-dependent birth and death rates. The horizontal axis represents the population size, N, and the vertical axis represents the per capita rate. Notice the downward sloping line starting at B0. This shows the birth rate dropping as crowding increases. The upward sloping line starting at D0 shows the death rate rising. The most important part of this diagram is where the two lines cross. At this exact intersection, the birth rate equals the death rate. If you follow the dashed line down to the horizontal axis, you will see this point is exactly the carrying capacity, K. This visually proves how nature forces populations into balance. We have covered a lot of ground today, so let us summarize the key takeaways. First, intraspecific regulation is the natural mechanism that controls a population's size through internal competition for resources. Second, as a habitat gets crowded, density-dependent mechanisms kick in, forcing birth rates down and death rates up. Third, this dynamic naturally leads to the carrying capacity, which is the maximum number of individuals the environment can sustainably support. Finally, the population stabilizes exactly when the birth rate equals the death rate. Understanding this delicate balance is the foundation of modern ecology, allowing us to protect ecosystems from collapse. You now have a solid understanding of how populations regulate themselves in nature.